While the world has been distracted by the noise of social media and the rise of chatbots, a silent revolution has been taking place in sub-zero laboratories and shielded data centers. We are standing at the precipice of the quantum age. Today, we are going to journey through the 11 most mind-bending, reality-altering milestones that have just occurred. These aren't just incremental updates. These are the tremors before the earthquake that will reshape medicine, finance, security, and our understanding of the universe itself. So sit back, open your mind, and let's count down the 11 breakthroughs that prove the future is already here. 11. EOS enters the arena. The birth of Ocelot. For years, Amazon Web Services (AWS) has been the silent backbone of the internet. But recently, they stopped being just a host for other people's technology and decided to build the brain of the future themselves. Enter Ocelot. Until now, if you wanted to play with quantum mechanics, you had to rely on specialized hardware startups. But AWS unveiled Ocelot, their very own superconducting quantum chip. Why does this matter to you? Because it signals a massive shift in intent. Amazon isn't doing this for a science fair project. They are doing it because they see the tidal wave of demand coming from industries you rely on every day. Think about the logistics of delivering packages to millions of doorsteps within 24 hours. Think about the complex financial models that keep your retirement funds stable. These problems are becoming too complex for standard computers. By building Ocelot in-house, Oz is telling us that the era of quantum is beginning. We are moving toward a world where a biotech startup in a garage can access a quantum supercomputer remotely to cure a disease, powered by a chip like Ocelot sitting in a server farm thousands of miles away. The barrier to entry is crumbling. 10. The art of circuit knitting, stitching the impossible. One of the biggest criticisms of quantum computers is that they are currently too small. They don't have enough qubits, the quantum equivalent of bits, to solve massive problems. But human ingenuity always finds a workaround. We call it circuit knitting. Imagine you have a puzzle that is too big for your table. What do? You break it into smaller sections, assemble them on different trays, and then stitch the final picture together. This is exactly what researchers are now doing with quantum algorithms. Instead of waiting 10 years for a massive, perfect quantum computer, platforms like Amazon Breakit are allowing scientists to chop up complex problems. They run the quantum parts on available, smaller chips, and then use classical computers to stitch the results together. This is a game changer because it accelerates the timeline. We don't have to wait for the iPhone 15 of quantum computers to start getting results. We can do complex simulations today. For you, this means faster advancements in battery technology. And material science are possible right now, simply by being smarter about how we use the tools we have. 9. Google's Willow, the endurance runner. Speed is nothing without stability. Imagine a sprinter who is the fastest in the world but trips over their own shoelaces every 10 meters. That has been the problem with quantum computers. They are incredibly fast, but incredibly fragile. They make errors. They lose their coherence or their quantum state very easily. This is why Google's recent demonstration with their Willow chip is so vital. Willow isn't just a processor. It's an endurance athlete. With 105 qubits, Google didn't just show it could calculate. They proved it could survive. They subjected Willow to extreme stability, testing heavy workloads, long sequences of code, and thousands of repeated experiments. The result? It held the line. It didn't collapse. This proves that we are moving past the experimental phase where quantum computers are delicate flowers that die if you look at them wrong. Willow demonstrates that we can build hardware rugged enough to handle the grinding, demanding computations required for real-world logistics or climate modeling. It is the difference between a prototype car and a reliable truck that can haul a load cross-country. 8 MBM quantum system. 2. The modular future. If you walk into a modern data center, you see rows and rows of servers working together. But quantum computers have largely been isolated, lonely chandeliers hanging in gold-plated fridges. IBM is changing that geometry with the quantum system too. This isn't just a chip, it is an architecture. IBM is debuting a modular system, essentially quantum Legos. It is composed of multiple cryogenic units, interconnected chips, and high-speed control racks that function as a cohesive whole. Why is modular the magic word? Because it allows for scaling. If you need more power, you don't just build a bigger chip, which gets incredibly difficult. You add another module. This parallels how we built the most powerful supercomputers on Earth today by clustering thousands of smaller processors. IBM is moving quantum computing out of the physics lab and into the supercomputer center model. For the global economy, this is the blueprint for the factories of the future, capable of processing data on a scale we can barely comprehend. 7. IBM Heron. Silencing the noise. Let's talk about noise in the quantum world. Noise isn't loud music. It's interference. Heat, vibration, stray electromagnetic waves, all of these confuse qubits and cause errors. If your calculator told you that 2 plus 2 equals 5 because it got too hot, you'd throw it away. IBM's Heron processor is the noise-canceling headphone of the quantum world. It utilizes tunable couplers. Think of these as gates that control exactly when qubits talk to each other and when they ignore each other. Previously, qubits were like people in a crowded room shouting all at once. The crosstalk was terrible. Heron allows researchers to turn the volume down on the chaos. By significantly reducing crosstalk, Heron boosts accuracy. This matters because you cannot run a long, complex algorithm like simulating a new pharmaceutical drug if your errors pile up halfway through. Heron represents the refinement of the tool, sharpening the blade so it cuts cleanly through the data. 6. Microsoft's long bet, the Majorana 1. While IBM and Google are racing with superconducting qubits, Microsoft has been playing a different, riskier game. They are betting on topological qubits, specifically the Majorana fermion. Think of a standard qubit like a spinning top. If you bump the table, the top wobbles and falls. That's an error. Microsoft wants to build a qubit that is more like a knot tied in a rope. If you bump the table, the knot doesn't untie. It is inherently stable because of its structure, topology. For years, this was just theory. But with the Majorana 1 prototype, Microsoft has made significant progress. They are hinting at a future where we don't need massive amounts of software to correct errors because the hardware itself is immune to them. If they succeed, they could leapfrog everyone. It would mean smaller, more efficient, and vastly more powerful quantum computers. It teaches us a valuable lesson. Sometimes the hardest path, the one that requires reinventing physics, yields the greatest reward. 5. The quantum microscope, nuclear spin methods. Now, let's look at an application that could save your life. We are seeing the rise of quantum nuclear spin methods to reveal molecular geometry. Current technology like MRI or X-ray crystallography has limits. It's like trying to read a book from across the room. You can see the shape, but you can't read the text. Quantum sensors use many body spin echoes to look at the interaction of atoms at a level of precision classical tools cannot touch. This is the high-definition revolution for chemistry. Imagine trying to design a drug to block a virus. You need to know exactly how the virus is shaped, down to the atom, to create a key that fits that lock. This quantum technique allows us to see those structures with unprecedented clarity. We are talking about accelerating drug discovery for cancer, Alzheimer's, and new antibiotics. It connects directly to our health and longevity, turning quantum physics into a healing tool. 4. D-wave and the false vacuum. Simulating the universe. Have you ever wondered how the universe might end? It's a heavy question, but physicists worry about something called false vacuum decay, a state where the universe is stable for now, but could suddenly collapse into a different state. Calculating this is a nightmare for classical computers because the math is overwhelmingly complex. Enter D-wave and the power of quantum annealing. Researchers recently used D-wave's hardware to simulate this complex physics phenomenon. Why does this matter to you other than existential dread? Because if a computer can simulate the fundamental forces of the universe, it can simulate anything. It proves that quantum annealers, which are different from the gate model chips Google uses, are incredibly good at optimization and simulation. This same technology that models the collapse of the universe can be used to optimize global shipping routes to reduce carbon emissions, or model the flow of financial markets to prevent crashes. It is about understanding complex systems that have too many variables for a human brain to hold. 3. IBM Condor. The 1,000 qubit milestone numbers matter. In the history of computing, we celebrate the moment we hit 1 megabyte or 1 gigahertz. In quantum, the magic number was 1,000 qubits. IBM's Condor chip has crossed that line. It is the first publicly revealed processor to house over 1,000 qubits. This is a psychological and engineering barrier. Skeptics said it couldn't be done, that the wiring would be too dense, the heat too great. IBM proved them wrong. Crossing 1,000 qubits is the Wright brothers moment, where the plane flies not just for a few seconds, but sustains flight. It proves that large-scale architectures are physically achievable. It is the stepping stone to the multi-chip clusters we discussed earlier. For the industry, this is the green light. It tells investors, governments, and scientists that the roadmap is valid. We are scaling up. 2. The death of hacking? Certified true randomness. We need to talk about your bank account, your passwords, your private messages. All of digital security relies on one thing: randomness. To encrypt data, computers generate random numbers. But classical computers aren't truly random. They are deterministic. If a hacker knows the algorithm and the starting point, they can predict the number. It's like a magician forcing you to pick a card. You think it's free choice, but it's calculated. A recent breakthrough with a 56-qubit system has produced certified true randomness. In quantum mechanics, outcomes can be genuinely, mathematically unpredictable. This system produced strings of numbers that are verified to be impossible to predict. This is the holy grail of cryptography. It opens the door to a level of security that is theoretically unbreakable. For banking, national defense, and your personal privacy, this is the shield of the future. It ensures that as computers get faster and hackers get smarter, our defensive walls get stronger, grounded in the laws of physics themselves. 1. The summit. Google achieves practical quantum advantage. And here we are. The number one story? The moment that changes the narrative from someday to today. Google has achieved practical quantum advantage. Using the Willow chip, Google ran the quantum echoes algorithm. They tackled a structured physics problem and didn't just beat a classical supercomputer. They annihilated it. The processor outperformed the world's best classical machines by over 13,000 times. This isn't a theoretical benchmark. This is a scientific, meaningful speedup. It marks one of the clearest examples that quantum hardware provides an advantage that classical silicon simply cannot match. It's the moment the steam engine beat the horse. It validates billions of dollars of investment and decades of research. This speedup suggests that for certain classes of problems like designing new batteries, optimizing logistics webs, or creating new materials, we are on the verge of leaving classical computing in the dust. So, what do we take away from this whirlwind tour of the quantum frontier? The story of these 11 breakthroughs is a story of convergence. Hardware is getting stable, Google Willow. Systems are scaling up, IBM Condor System 2. Access is democratizing, Oz. And applications are becoming real, chemistry, randomness. The lesson for us is that technological change happens slowly and then all at once. We are in the all-at-once phase. For you, the viewer, this is a call to curiosity. The skills of the future will involve understanding how to work with these probabilistic machines. Just as the internet changed how we do business, quantum will change how we solve problems. It invites us to look at the world not as a rigid clockwork mechanism, but as a fluid, interconnected web of possibilities. Ask yourself this: if you had a tool that could simulate 1,000,000 outcomes for your life in a second, how would you change your decision-making? The quantum age isn't just about faster calculators, it's about a new way of thinking. I hope this journey into the quantum realm has sparked a fire in your imagination. The future is bright, it is fast, and it is weird in the best way possible. If you want to stay ahead of the curve and understand the technology shaping our world, hit that subscribe button, ring the bell, and join us as we explore the unknown together.